Hello, my name is Arnold Filzer, and today I'll tell you about cloud embeddings into trees and low Treewidth graphs. This is a joint work with Hanley from UMass. So today we'll talk about metric embeddings, which are simply a function between between the points of two metric spaces. So basically, in this talk, we'll like to preserve the distances of the metric space X inside the metric space Y to which we send it to. We say that embedding F from X to Y has distortion T, if for every pair of points X and Y, the distance between their images does not decrease and is increasing by at most a T factor. So, I mean, the most basic idea in metric embeddings when you use them is that you have some hard problem in metric space X, you send the points to Y, which supposedly will be a simpler metric space, you solve the problem in Y, and then you pull the solution back, and hopefully you'll get some sensible solution using this way. So, for example, for now, you can think about this metric space X as the shortest path metric of some complicated graph, and Y will be simply a tree metric. So now that the tree metric is very desirable host metric because it's very kind of basic and simple, and there's lots of problems which become easy once they are in trees. However, the problem is that actually trees are not very rich metric space, and specifically, even if you looking on this n cycle, already every embedding into a tree requires distortion n-1, which is quite bad. However, let's think what will happen if we simply delete a random edge. So the result will be that for every pair of neighboring vertices, vi and vi plus 1, the expected distance between them, the resulting tree, will be at most 2. So there's some probability of, unless you delete this edge, distance will be 1, if you delete the distance will be n-1, so in total the distance in expectation is 2, and the linearity of expectation actually for every pair of vertices, the distance, the expected distance will be at most twice the original distance. So this quite looks very good, right? It's not a real embedding, but some stochastic embedding, but you get something very nice. And as was shown by Fakar-Shopel, Raman Talwar, this is a general phenomena, proving some work of Bartel, and specifically they showed that every endpoint metric space embeds in the distribution over dominating trees with expected distortion log n. So let's break down this theorem. So we have some metric space X, and there's a distribution over embeddings of this metric space into trees. Each such embedding is dominating, that is for every pair of points u and v, and for every tree t in the distribution, the distance in the tree is at least as large as the original distance. And in addition, for every pair of points u and v, the expected distance is at most log n times larger than the original distance. And therefore, it's very nice. This embedding enjoyed tremendous success. However, one should see there's a compromise here. The guarantees are only in expectation. There will be some pairs in which the distortion will be essentially unbounded. Okay. So in order to kind of cope with this problematic guarantees, there was people studied these Ramsey type embeddings, which in a sense have this idea that every big enough object contains a structure subset. And specifically, note that if you're looking on this cycle and we delete this edge vi plus 1, then while it's true that the worst case distortion is I minus 1, in this entire area, which is far away from this edge, the distortion are quite small. And specifically, if we look on all the vertices, which are at least epsilon n distance from the deleted edge, and denote this by the set m, then for every such pair of vertices, the distortion actually is most 1 over epsilon. And furthermore, the set m is quite large, of size at least like 1 minus 2 epsilon times n. And this is kind of said that is for a very large portion of your metric space. In this case, you enjoy a very small distortion. And this could be a general thing, as was shown by Manuel Naor in previous work. For every endpoints metric space and for every parameter k, there is a subset m of size at least n in the power of 1 minus 1 over k that embeds into a tree. The distortion is typically k. And so here we have a metric space. You can find some subset m of this size, such that for every pair of points, and send this set m into a tree, such that it's dominating, that for every pair of points, the distance is at least as large as in the original metric space, and it's distorted by at most a multiplicity factor of k. And again, this is very nice and useful. However, the compromise here is you have only partial guarantees. I mean, there will be some pairs that you don't even embed or don't say anything about them. And to kind of cope with this compromise and the previous one, in this work, we introduced clan embeddings. And the idea is that we would like to get worst case guarantee for all vertex pairs. And to compromise for this, we'll duplicate vertices and therefore we'll be able to prove more. And specifically in this end cycle idea, so we rip here the cycle off in, say, at point I, and when we add some copies of these vertices here, kind of there will be some vertices, for example, this vi plus 1, which will have 2 copies. Let's try to formalize it. So what we'll have here is a one-to-many embedding. Specifically, it's embedding from a metric space to subset of points in the metric space Y. So each point X will map to a subset in Y. And the requirement is that for every point X, the subset f of X will be non-empty. And for every 2 points X and Y, their subset f of X and f of Y will be disjoint. Okay, so this is one-to-many embedding. And this subset f of X will be called the clan of X. And each X prime will be called a copy of X. So this kind of a clan, and the members of the clans are called copies. So we'll say that a one-to-many embedding is dominating if the distance, if for every pair X and Y, the distance from every 2 copies X prime and Y prime of X and Y will be at least as large as the original distance in the metric space X between X and Y. And in addition, for each clan f of X, for each clan f of X, you will choose a chief, he of X, which becomes the most important vertex in the clan. We should have a special role, as you will see. So in this example here, the clan embedding is from the cycle graph to the path graph. For every vertex vi, this clan consists of the vertices vi tilde and vi prime. So for some of them, it's only vi tilde. So for example, for vi plus 1, there's these 2 vertices, while say for v0, there's only 1 vertex, there's no prime. And the chief, chi of vi, will always be vi tilde. So this kind of the red, whereas here, this is the chiefs. Well, these are copies which are non-chiefs. So this is kind of the clan embedding. And the clan embedding is just a pair of a one-to-many embedding F and chief's choice, he. And we said that clan embedding F, he, has distortion T if for every pair X and Y, the minimum distance between a copy Y prime of Y and the chief of X is at most T times larger than the original distance. Yeah, so again, the minimum distance between a copy Y prime and the chief is at most T times larger than the original distance. So note that this definition is asymmetric in the sense that there's different roles here from X and Y, but know that you can use it, it should hold for every order pair X and Y. So you can also use it for YX. So it's kind of working this way. And let's see this example. So here, the distortion will be kind of the worst case will be on this pair vi plus 1 plus epsilon n, and vi, because this is the first vertex that doesn't have 2 copies, but only 1, and distance will be kind of to get from here, from every copy of vi plus epsilon n to vi, you need to go this entire path, which is a distance about 1 plus epsilon n, well, it's supposed to be epsilon n, if you go like here, and therefore the distortion is 1 over epsilon. This is the worst case, and that's it. But know that if you choose I uniformly at random, then the expected size of a clan is only 1 plus 2 epsilon, because only these vertices here, like kind of this area here, have 2 copies, only like a 2 epsilon and stretch. And while the worst kind of the distortion guarantee is 1 over epsilon, in the worst case for all the vertex pairs. Okay, and so this is kind of the cycle, and our main result is a general case of this kind of phenomenon of clan embedding. And so we show that for every metric space X, then points, and for every parameter epsilon, there is a distribution D over dominating clan embeddings into trees. So there's like kind of this thing, like in the FRT, there's a distribution over clan embeddings such that, so first, for every clan embedding F here, remember it's a pair in the support, the distortion is log n over epsilon, and this is a worst case guarantee. So for every embedding, clan embedding F here, and for every pair X and Y, the distortion, kind of the distance between a copy of Y to the chief of X, will be at most log n over epsilon times larger than the original distance. So again, this is the worst case guarantee. And in addition, for every point X, the expected size of the clan of X will be at most 1 plus epsilon. So there will be some embeddings in distribution where there will be more than one copy, but in most of them, actually, there will be only a single copy for X. So again, this kind of the payment here is in the number of copies instead of in the distortion. And there's also a version when if you want to get small distortion, it's possible, specifically for every metric space X and endpoints, and for every parameter K, because this is the distortion parameter, there is distribution D over dominating clan embeddings into trees, such that here you have a worst case distortion guarantee of K, and the expected size of the clan of each vertex is bounded by n to the 1 over K. So yes, obviously the clan here is much larger, and you don't expect to have only a single copy. Okay, so this is clan embeddings, and know that the compromise here, of course, is that it's not a real classic embedding. So in a sense, the way we think about this is there's a trinity here of tree embeddings, when this kind of more classic ones, stochastic and Ramsey, and now we have this new clan that closes this trinity, and each one of these tree embeddings have a different compromise and different points of advantage. So specifically, the stochastic embeddings satisfy all vertex pairs, and it's this classic one-to-many embedding. However, it sends only 1 point to 1 point. However, it doesn't have a worst case guarantee, it's only expectation. The Ramsey type embedding has a worst case guarantees, which is great, and it's one-to-one embedding, but it does not satisfy all pairs, only some partial pairs. And finally, the clan embedding is both worst case and satisfies all pairs. However, the compromise is that it's not one-to-one embedding. The rest of our program will be to show some additional clan embeddings of minor free graphs into low Treewidth graphs and show some applications of all these embeddings. So recall the FRT stochastic embedding. Every endpoint metric space embeds into trees with expected distortion log n. This very successful embedding is tight. That is, you cannot improve this log n distortion. So the initial question to ask is, if I have a special graph family, could I do better than general graphs? The special graphs here, I mean like planar graphs, minor free graphs, or bounded Treewidth graphs. So if you don't know what Treewidth is, it's some property which measure how a graph is like a tree, how much tree-like is a graph, and it's a very beneficial property for algorithmic design. Yeah, so let's back to our problem. Suppose you have a planar graphs. Could you embed it better to trees than general graphs? Unfortunately, the answer is no. Okay. What if I allow you, if I want to embed not into trees, but to low Treewidth graphs, which are supposed to be more representative than trees? Could you do better? And the answer again is no. And specifically, as Chakrabarty et al. Showed, there is some specific n vertex planar graph G, such that every stochastic even embedding into square root n, if the graph is really smaller than square root n, must have expected distortion at least log n. This is unfortunate, and this kind of seems to close the question. But now, as Fox, Epstein, Klein, and Shield show in previous results, one can construct a different type of embedding. And specifically, they show that every planar graph G with diameter D, and for every parameter epsilon, one can embed this graph into a graph with Treewidth polynomial in 1 over epsilon with additive distortion epsilon D. So let's understand what's going on here. So we have some parameter, new parameter D here, which is the diameter, the maximum distance between any two vertices in the graph G. And we have an embedding from G to a graph H, where H has Treewidth polynomial in 1 over epsilon. And for every pair of points U and V, the distance in H does not decrease and is increasing by at most an epsilon D additive factor. So this might seem crude at first glance. However, they showed very nice applications to Baker metric problems and vehicle routing. Okay, so this is great. However, once you have any results for planar graphs, of course, the next question is, what about minor free graphs? Could you do the same? And usually the answer is yes. However, here, surprisingly, the answer was no. And as we showed with Cohen, Dad, Klein, and Lee, there is some K6 free graph. So already as you start being planar, everything is fall apart, such that every classic embedding, like this embedding is classic, so every classic embedding into square root into graph is true is smaller than square root n, incurs additive distortion at least D over 20. I mean, some constant D. And I mean, you cannot go to epsilon D as one might wish. Okay, so this is bad. However, once a classic embedding fails, the natural question to ask is, what about stochastic? Could you do it stochastically? And as we showed there, the answer is yes. And specifically, for every parameter epsilon at any endpoint KR-free graphs with diameter d, one can stochastically embed it into distribution over graphs with Treewidth log n over epsilon square with expected additive distortion epsilon d. So this is weaker than Fox-Epstein-Tal results in two senses. So first, the Treewidth depends on log n, while here it was independent of n on the size of the graph. And this is classic. Well, here we have expected additive distortion. And just let's break it down. This means that for every pair of vertices in the support, the distance between them in the graph does not decrease, and the expected distance between their images in all distribution will be at most the original distance plus an additive factor of epsilon d. And given this paper, of course, once you have the stochastic embedding, a natural question, we want to get our entire trinity, Clan and Ramsey. And in this paper, we did get these embeddings, both Ramsey and Clan, and we'll talk about the Clan embedding. So let me parse it for you. So for every epsilon, we show that for every parameter epsilon and every endpoint KR-free graphs with diameter d, there is a distribution over dominating Clan embeddings into graphs with Treewidth log square n over epsilon square, such that, so now the Treewidth is a bit larger. So first, the expected size of each clan is almost 1 plus epsilon. So recall this is a one-to-many embedding. Each vertex go to maybe multiple subset of vertices, and the expected size of every clan is almost 1 plus epsilon. And the second property is the worst case distortion guarantee, and specifically for every clan embedding in the support, which is a pair of one-to-many embedding and choice of chiefs, and every pair of vertices U and V, the minimum distance between a copy of V to the chief of U will be at most the original distance plus an additive factor of epsilon d. So let's see an example. So this is some graph with actually high Treewidth, and we embed it using a clan embedding into graph with small Treewidth. So you can see kind of this graph indeed has a small Treewidth, and this is a one-to-many embedding. So for example, this single vertex here will go to this subset here, this vertex here go to this subset, and this vertex only one image. And note that this black here, this will be the chief, and this will be just the copy. And again, this is the chief, this is the copy. And notice the kind of it's kind of the image of the vertex are not supposed to be close to each other because you want to catch a large distance. And specifically, because you cut here in a sense, you want to compensate for the loss of this edge, and therefore you put a copy near to your previous, in a sense, neighbor. Okay, so this is our embedding of minor-free graphs into low Treewidth graph. Next, we will see some applications. So first, we'll start with the metric dominating set problem. So in this problem, we're given some metric space, and the goal is to find the dominating set, a row dominating set. So specifically, we're given set A. A set S is an A row dominating set if for every point X in A, there is some point Y in S, a distance at most row from X. So let's see an example. So this is some graph, it's a metric space that shows pipe metric, and you have a set A, the purple set here, and some parameter rho. And the goal is to find a set that will dominate A, the row dominates. So for example, this single vertex B is a row dominating set because every vertex in A, the distance is most 3 row from B. This is another example, because again, every vertex here, the distance is most row from this green set S. And the goal is we're given some set A and some measure mu over the metric points. And the goal is to find a row dominating set of minimum measure. And in this example, this will be the optimal row dominating set. So note that the classic dominating set problem will be simply when the shortest path metric is of unweighted graph. The set A is the entire space, rho equals 1, and mu is the uniform measure. And generally, I mean, this is the dominating set problem. However, in minor free graphs and planar graphs as well, this problem becomes interesting with general rho, because now it's kind of, in a sense, the dependencies between different vertices is not planar or minor free anymore, because there might be like big cliques and many dependencies. However, as the underlying metric is minor free, you still often can do something much smarter. Okay, so let's see, and indeed, Fox-Epstein et al. Was able to use their classic embedding of linear graphs into Treewidth graphs to obtain the first PITAS, polynomial approximation scheme for this problem. Specifically, they get a bicriteria approximation scheme, 1 plus epsilon plus epsilon, in a time which is 2 poly epsilon 1 over epsilon. And by bicriteria here, I mean they were able to find a set which is 1 plus epsilon row dominating, not row dominating, but rather 1 plus epsilon row. And the measure of the set will be at most 1 plus epsilon times larger than the measure of the optimal set of the original row dominating set problem. Okay, so this is it was nice. However, now of course we'd like to get the same for minor free, but the stochastic embedding that was known before this work will not do. And the problem is that, I mean, the first thing, of course, do is to embed the graph in the Treewidth graphs. And once you have a classic, you just can solve there and pull the solution back. But once you have a stochastic embedding, it's not strong enough because you need to find an actual dominating set, not something which work only in expectation for some big portion of the pairs. And fortunately, cloud embeddings save the day. And specifically, you can know that cloud embeddings are enough because now you can just embed and it's enough to dominate the chiefs of the set A, and you are guaranteed that indeed some good dominating set will exist because the image of all the original dominating set will now be a dominating set. Okay? And what we actually were able to show is a quasi-polynomial bicriteria approximation scheme. Again, it's the same 1 plus epsilon bicriteria. And unfortunately, we get only a quasi-polynomial time because of our log square since Treewidth. It's not enough to get the real PITAS. But still, the first thing that we know for minor free graphs, and it will be very nice to improve. Next, we'll show applications of cloud embeddings to compact routing schemes. So recall our cloud embedding was that the trees was that every matrix poise and for every parameter epsilon, there is a distribution D over dominating cloud embeddings into trees, such that every embedding in the support has worst case distortion log n over epsilon, and the expected size of every vertex is at most 1 plus epsilon. Okay, so this is kind of embedding into trees, but these trees, I mean, completely general, actually it's ultra metrics. And we also have a kind of spanning version of this theorem where we get some sort of subgraph. I will not give you the exact definition, but in a sense, this is a tool that you actually can use to make routing decisions. And we'll show how. And it's spanning. And the caveat here is that you have this kind of additional log n factor in distortion, which would be nice to remove. And otherwise, it's the same. Okay, so let's define the compact routing problem. So here you have some huge network, and each server, each node contains a server, and the goal is to route some packets throughout the network. However, the problem is the network is huge, and it's completely unfeasible to store the entire network in each node. So we need to make some decision based on partial information. And consider the following scenario. So you have some node, it has some label, the destination, and some content of a packet it will send, and it starts to sending this packet throughout the network. And in some middle point, there is some this node here, which receives a packet which consists of a label and some content. And based on this label and some small routing table it stores locally, it needs to make some routing decision. And we wanted to make this decision fast. And eventually, hopefully, the packet will actually reach the destination. So in order to keep all other parameters small, we'll allow some stretch. And specifically, instead of this requiring this packet will go from the initiating vertex to the destination in the shortest path, we'll allow it to go in a path which is at most some factor k times larger. So this is the problem, and if your graph is a tree, so of course there's a great solution by Torp and Svik, who showed that for every tree, one can construct a routing scheme with stretch 1. So this is actually the shortest path. The label size is log n, the table size is constant. So let me note that we measure size here in words. Each word is log n bits, and decision time is constant as well in each node. So this is a great routing scheme. And now, using our spanning clan embedding and the routing scheme for trees, one can construct a very simple and nice routing scheme. So consider this clan embedding from this graph into this tree. And now there's some copies of some vertices here. And the idea is of the routing scheme is as follows. So first you construct a cloud embedding Fhe into a spanning tree T. Now for this spanning tree T, we construct a routing scheme, forgetting about where this tree comes from, using Treewidth. And now when you want to route some packet from V to U, so we'll simply look on all the copies of V and choose the best copy and send the packet from this copy V prime to the chief of U to hit U using this tree. So we'll just think that we live in a tree, and that's it. And using this, we'll make the routing decision. So of course, there's some more details which you are welcome to see in the paper, but this is the basic idea. This is a very efficient routing scheme. So now the stretch will be somewhat large, log n log n, because this is a stretch of the cloud embedding. However, the label will be very short. For the only label you need is kind of the label of the chief of U, so the label of each vertex will be simply the label of its chief in the Treewidth routing scheme. The table will be just constant because it's constant here. However, of course, and decision time will be constant. However, note that actually the size of the table is constant only in expectation. So if your number of copies is constant, this will be constant because you actually need to store the routing table for each copy. However, for most of the vertices, of course, will be constant, and kind of the amortizable order vertices will be only n. Okay, so this is our routing scheme. So just to compare it to previous state of the art. So in the regime, when you want to stretch log n, so here we improve over previous work of Abraham et al, getting the same label size and getting a table size which is just a constant, while they have log n. However, of course, this is only expectation. Well, this table size is worst case. Note that our labels are also worst case. And in the log n regime, there is some two works also Abraham et al and Chechik. So we improve both of them. Here, the work of Chechik, we get the same table and stretch while improving the label. While comparing to Abraham et al, we have the same label, but improving the table. So we improve over both of them. However, of course, we have this expected table size, not worst case like previous works. Okay, so this is about routing. So let me wrap up with some open questions. So recall our result of cloud embeddings of minor free graphs into long Treewidth graphs. Here we show that every KR free graph with diameter D could be embedded into distribution over graphs with Treewidth log square n over epsilon square with this expected clan size 1 plus epsilon and worst case additive clan distortion of epsilon D. So it will be very nice to improve the Treewidth here, which is kind of the only parameter you really can improve. And this we saw, for example, if you remove this dependency on log n or even get it log n here, it's supposed to give you a pitas instead of a q pitas that we currently have. This is the first open question. The second open question was regarding this spanning cloud embeddings into trees. So we have this annoying log n factor here in distortion. It would be very nice to remove it and get k, so you cannot go beyond k. This will be optimal. Our usual cloud embeddings are optimal. But let me just say that we have similar problems in other type of embeddings, for example, even in classic stochastic embeddings into spanning trees, there's log n factors, also in the Ramsey type. So every time you have subgraphs and spanning versions, there's log n factors pop up, and we currently don't know how to remove it. But the final, and I think most interesting open question we're leaving for you for today will be just find more applications for this new tool of cloud embeddings. That's it. Thank you for your time.